Today, I'm going to deal with a very interesting subject that very few engineers are aware of. And that's the subject of pile testing. Normally, engineers assume that when design a pile, they get a pile. But sometimes the story is a little different, as we'll see. I'm going to speak shortly about types of deep foundations, or in short, piles, defects in deep foundations, and about pile integrity testing, which is the majority of this presentation. I'll mention direct methods for integrity testing and indirect methods. And among these are the PET, the pile echo testing, CHUM, crosshole testing, the BIT testing pile verticality, and the PSI testing hidden piles, piles which are unseen at all. I'll try to put some order in three terms that are very frequently mixed. And these are anomalies, flaws, and defects. And I hope we'll have some time for questions and answers and some concluding remarks. First of all, what is a pile? A pile is a slender, deep foundation, either prefabricated or cast in sheeting. And I don't know what you know about the oldest profession, but I think piling could be the oldest profession. This is a sample of a wooden pile that was discovered in London and dates back about 6,000 years ago, more than 6,000 years ago, and it's still in existence. Today, we have not only wooden piles, we have many other kinds of deep foundations. I'm not going to deal with each kind separately here. That's a different subject. But we are having two different families of piles, displacement piles and replacement piles. And honestly, all kinds of piles may have their defects. Why? Because the final product is invisible. In normal situations, this is what we see above ground, and this may be 1 or 2% of the whole volume of the pile, the rest of which is buried in the ground. And we have a question: what do we have below ground? Here is an example of some piles that were exposed during excavation. And you can see that the quality of these piles is not very good. At least this contractor put some steel in the ground. Some contractors even do not put steel in the piles. This contractor was very clever. He knew that he is going to produce the piles in sandy soil, which is not very stable. So we used some casings out of cardboard. But you see that below the casing, there was some collapse, and of course, the pile is not good. Here is an excellent pile, which was produced by an excellent contractor. Unfortunately, the contractor didn't realize that he hit a live sewage line, and the flow of the sewage water ruined the pile, which we had to repair later. This is a pile cast with polymer slurry. Very sophisticated support method, but sometimes it doesn't help. This is a diaphragm wall for a basement, and it was cast with bentonite to support the excavation, and still the end result was very unsatisfactory. Here's a diaphragm wall cast with polymer slurry. Different technique, but the results were not much better, even worse. Now, even under ideal conditions, when you have stable ground, hard clay, no groundwater, no chance for collapse, you can have this situation. Or this one, which is almost a complete discontinuity of the concrete. Here's another example of a problematic pile. This bridge was produced top down, which means the piles were first constructed, then the top concrete was poured over the piles, the pavement, and then excavated below. And only when they excavated below the pavement, we found that these piles, at least one of them, was of very poor quality. Now, how much flaws or defects do we have in piles normally? I collected some information from our files and from literature. For instance, 1.7% of piles with flaws, this is from the early 70s and 80s of the last century. Now, this is a very low percentage, and for two reasons. First of all, at that time, the testing instrumentation was very rough and very inaccurate. So there were many defects it couldn't discover or expose. And the second reason for this low percentage is that in this case, the testing was done by the contractor who tested his own piles. And of course, it's very difficult to be very neutral and very objective under these conditions. No contractor likes to admit that he's producing faulty piles. But when we go to different places in the world, California, somewhere in Asia, Italy, Israel, we see that the percentage of piles with flaws can be much, much higher. And it can be alarming. And this raises the question of pile integrity. There are many definitions of pile integrity. The way I define it is meeting the requirements of the project with regard to material and geometry, which means we have drawings and we have the specifications, and these determine how the pile should look like and what is the material it should be constructed of. Now, sometimes we have integrity problems, like flowed material. Here we have a pile produced of good concrete, and somehow here we have a pocket of poor concrete, result of poor construction technique. Here is a soft bottom, which means during casting or some collapse, the contractor didn't clean the bottom very well, and we have the bottom or the toe of the pile consisting of soft clay or soft debris. Now we can have an abnormal geometry. For instance, a pile can be short. Sometimes because the drilling equipment was not powerful enough to penetrate the hard soil. Sometimes because the contractor didn't have a strong enough machine or just wanted to save, assuming that he will never be checked. Here we have necking. This is a collapse that happened during casting, and instead of concrete, we have here mud or some foreign material, and we get an abnormal geometry of the pile. And sometimes we can have an inclined pile. A pile which had to be vertical is not very vertical. And this is, of course, also contrary to the specifications. Now, we have integrity testing techniques, which I'm going to tell you about today, and they are used to discover defects before they can cause any damage. If you build a building or a bridge or any other structure on faulty piles, they can cause a lot of damage. If you manage to locate and expose these piles before you build on them anything and before you apply the load, you can avoid a lot of damage. There are two families of integrity testing methods. The first one and the oldest one is excavation. If you suspect that your pile is not very sound and there may be some defects, you can just excavate around it, and sometimes this is what you discover. Of course, you must have some suspicion that something is wrong with this pile. Of course, you cannot go very deep with this method, especially if you have high groundwater level. The other direct method is core drilling. Here you can go very deep inside the pile and get a very good sample of the concrete. Of course, this relates only a very small percentage of the cross-section of the pile. In addition, we have the indirect methods. And here we have two families of methods. We have long waves and we have short waves. On the left, we see how the long wave behaves in the pile. It can move only in one direction, either up or down. The short waves, or the ultrasonic waves, can behave like a mouse. They can go up and down, sideways, in all directions. So we have two kinds of indirect methods, the long waves and the short waves. The first method is the sonic method, or the sonic echo. So we'll see soon a short video showing how this method is applied on site.
PET, Pile Eco Tester, Low Strain Impact Testing. The mission: test the integrity of 12 concrete piles on this construction site. The tester goes to the first pile and prepares the top for testing. A small amount of special putty is attached to the bottom of the PET. The PET is pressed against the pile top. The top is lightly hit with the hammer. A compressive wave travels down the pile and is reflected back from the toe. The blow is recorded on the screen. Good pile. The next pile has a defect that reflects the wave. The reflectogram on the screen shows a necking at a depth of 5 meters. The test results are now analyzed in the office and the report produced. The PET, your compact yet powerful tool for testing the integrity of deep foundations. Thank you.
This, in short, is the long wave method, the PET. The instrument works very well with a smartphone as a data logger. So what you see here, this can be a smartphone or a tablet. And if you have a smartphone, you can use all the other properties of the smartphone. For instance, take a photo of the pile, the top of the pile, or register the GPS coordinates of the pile. And of course, you can save the results you get in cloud, and therefore they can reach the main office on the other side of the globe immediately. So you don't have to wait for the results until you return to the office. Now, I'd like to present to you the PileWave program. This is a program that simulates the test. For instance, here is a sound pile. This is the time axis, and this is the depth. You see that the wave caused by the hammer blow goes to the toe of the pile. It is a compressive wave, and it is returned, reflected back as a tensile wave, and pulls the top of the pile a little bit down. Now, what happens if we have some necking? Smaller cross-section. We can show this with our mouse. Now we have a pile with a small defects close to the bottom. What happens if we hit it? Press start. You can see that because we lose a lot of energy passing through this defect, the toe reflection here is very weak. So we can apply some amplification. On the other hand, if we have a bulging here, you see a larger section, because here we had some collapse during drilling before we constructed or we poured the concrete. We press start. And here we have a very nice toe reflection, and we see that now this graph is going first up and then down, which means that we have a larger cross-section. Now, the PileWave program can be run on our website. It's free for all, and it's very good education tool. Present. Please be patient, just a moment. As I said, high tech. Okay, now we can see some results. This is a result of the test of a good pile. We see the hammer blow here, that's 0. We see the toe reflection here, and in between, it's pretty straight. No special event. Here we see that the graph goes first down and then up. Means here we have a necking or a smaller cross section. And here we have the opposite. We have a bulging, a large cross section here. Now the PET has also a signal matching utility in the software where if you match your result with the results from a synthetic pile and you have a good match, you can have a good guess what the shape of the pile is. In this case, this is a pile with a larger cross section. Now, this method can find the length of the pile, inclusions of foreign material, horizontal cracking, if there is, joint stage concreting. If you pour the concrete, wait some hours, and then continue concreting, you can have some separation here. Large, abrupt changes in cross-section, like this. And distinct changes in soil layers. This really is our biggest problem. If, for instance, the pile is cast in ground and then penetrates rock, the rock will produce a different kind of toe reflection. Of course, the PET cannot find anything if the top of the pile looks like this. So this is really a very poor technique to prepare the piles for testing. Advantages of the pile, of the sonic test, sorry. First of all, it's quick, it's inexpensive, it's universal. It can be used on concrete piles, wooden piles, even steel piles in certain cases. And there is no pre-selection because you don't need any special preparation. You can test any pile. The problem of the PET and all other instruments that are operated and working on the same principle is that there is limit to the depth to which it can penetrate. And the limit is determined by the slenderness ratio, L, the length of the pile, over the diameter. Now, SPT 5, standard penetration resistance of 5, soft soil, you can test piles up to 50 or 40 to 50 diameters deep and still get reasonable results. Of course, if you have a SPT of 30 or 40, you cannot go deeper than 25 or so diameters into the ground. This is a very interesting graph. The test duration in this method. The method, as I said before, is very fast. In 30 seconds, you can test about 65% or 2/3 of the piles within 30 seconds net, not counting the time it takes to move from one pile to the other. And you can test 90% of the piles in less than 2 minutes. These are results taken from about 70,000 piles from all over the world. So the method is very fast. There are situations where the sonic testing or the PET is unsuitable at all. For instance, if you have large piles carrying heavy loads. In this case, your method using long waves is not accurate enough. It doesn't have the resolution you are looking for. Here is another example where you cannot use this method. Sometimes when you have to produce piles inside the urban area in time, the site is very small. You cannot move around very well with the drilling rig. So what you do, you start drilling the piles from the street level here, and you cast them only to the basement level. And then you can start drilling, and you don't have to operate your large drilling rigs inside the crowded basement. Of course, this kind of pile cannot be tested with the PET. Here's another example. If we have rocky terrain, and above which we have fill made out of rock particles, the rock particles produce a lot of reflections. The rock has a lot of friction, which prevents the penetration of the signal. And this is another example of a diaphragm wall. Diaphragm wall is not a one-dimensional element. So the theory behind the PET doesn't apply to diaphragm walls. And we have to use a different method. The different method we use here is the CHUM, which we'll see soon in the video.
On this site, large diameter bored piles were constructed. On the surface, they all look perfect. But are they? CHUM, compatible with ASTM standard D6760, looks for the subsurface imperfections through the access tubes installed. Depth meter pulleys are placed on top of the water-filled tubes. Ultrasonic dual-function transceivers are lowered into the tubes. And lowered together all the way to the bottom, which may be 100 meters below ground level. When the sensors are level, the computer connected to the CHUM gives the order pull. While both cables are pulled together at a speed as fast as 2 meters per second, the location of the sensors is shown on the screen in real time. Ultrasonic pulses are continuously sent from the emitter to the receiver, and anomalies, such as increased arrival time or lower energy, are immediately displayed. CHUM automatically adjusts signal gain for optimal signal quality under variable conditions. CHUM also supports 2D and 3D tomography. Both sensors exit the access tube together, and the ultrasonic profile is already on the screen. First arrival time, relative energy, wave speed, and the waterfall presentation. Other profiles are logged the same way. The data is analyzed by the engineer who checks for any inconsistencies, adds his comments, and prints the report. This, in short, is the CHUM, our Crosshole ultrasonic monitor. It is portable, rugged, and productive. Due to the use of a detached computer, the CHUM will never become obsolete. Thank you.
By the way, when saying rugged, I recently saw a system which we sold 10 years ago, and it's still in action, working every day of the week. 5 or 6 days a week, 10 years. So it's pretty rugged. Now, what are the components of the system? Of course, we have the access tubes in the pile. We have the CHUM and the computer. By the way, all our systems have a separate computer, not embedded in the CHUM, and therefore, after 10 years, the CHUM can use a new computer when all other systems that are 10 years old have a computer long ago does not function. We must have a depth meter to monitor the depth of the sensors, which we have hanging from the cables. Now, after reaching the bottom, we pull both emitter and receiver together. Now, how many access tubes do we need? If we have a small pile, we don't have room for more than 2. A larger pile, 3, 4, 5. I even saw some very large diameter piles, 3 to 4 meters in diameter, huge piles with up to 10 access tubes. ASTM standards say that you use 1 tube for each 30 centimeter diameter. So if you have a 1 meter diameter pile, you need 3 tubes, 1.5 meter, 5 tubes. In the Far East, which means China, Vietnam, Malaysia, normally they use 4 tubes regardless of diameter. Even on very large piles, they use only 4 tubes. I don't know what's the situation in Indonesia. Now we said we have an emitter or transmitter sending the ultrasonic pulses, and this is what the receiver is getting. This is the time base. Here, the emitter is producing the pulse. While it's traveling to the receiver is stationary. And then it starts getting the waves arriving. The first arrival time, or in short, Sept, is recorded by the system automatically. How are the results presented? First of all, as I said, the Sept in microseconds. The relative energy, important parameter. We can calculate immediately the apparent wave speed if we take the separation of the tubes and divide by the time. And we have the waterfall presentation. All these are requirements of the ASTM standard. And here is a typical result. You can see immediately the red line is the Sept. You see that at this depth, between 3 and 4 meters, the Sept is becoming very large, while the blue line, the relative energy, is becoming very small. This means that here at this depth, we have a discontinuity or a defect. Now, if we want to know more about this defect, we can do a tomography. Tomography means looking at the defect not only in the horizontal direction, but also from diagonal directions, above and below. And then we can plot the shape of the defect on the screen. In this case, the system is the same one, but we have to use 2 depth meters. So the system will know at each moment where each of the sensors is. We have several systems or several algorithms for calculating the result. Here is one of the methods, plotting the results, and you see that with the 2-dimensional tomography, you can plot the horizontal dimension of the defect, not only the vertical, as in 1-dimensional testing. So this is the result of one algorithm. This is another one. Here we have some shade, some blowing of the horizontal defect. Here you see quite well how the defect looks like. both in the vertical and horizontal direction. Now, the CHUM is also a utility for calculating a three-dimensional tomography, where we take the results of all the tubes and combine them to get a three-dimensional picture of the pockets of foreign material or defects, if you like. We can have horizontal cross-section at any desired level, and we can have a vertical cross-section in any direction. The system also measured the relative strengths of the cross-section. And this is something that structural engineers would like very much to know if they have a problem in the pile. How much the cross-section is still effective. So our 3D tomography provides all the answers. Now, a few words about three terms that are very often misused: the anomalies, flows, and defects. And I must admit that even used testers and engineers with a lot of experience do not know the difference. Now, here are the definitions. Anomaly is any irregular feature in the non-destructive results. An anomaly can be due to testing instruments like noise, means use, access tube debonding. If you use steel access tubes, normally you don't have a problem. But in America, they like to use plastic access tubes, and the plastic tubes, the PVC, don't adhere too well to concrete, and there is some debonding. And even a millimeter separation between the tube and the concrete creates an anomaly. And as we said, surrounding soil can influence the results of the PET. And of course, the anomaly can be the result of an actual flow or defect in the pile. So not every anomaly is also a flow. What is a flow? Any deviation from the planned shape or composition of the pile, which does not necessarily detract from the pile's performance. So if you have a very small clay pocket close to the bottom of the pile, and the pile is a friction pile, not an end-bearing pile, this may be a flow. It does not detract from the pile's performance, and that's very important. On the other hand, the defect is a flow that, because of either size or location, may affect the pile's capacity or durability. So if you have a large flow close to the top, where the stresses are the highest, you can have a defect. Now, what do we do with flows and defects? The test laboratory, first of all, is responsible for reporting anomalies, all anomalies, and for assessing which anomaly comprises a flow. The geotechnical engineer and structural engineer are jointly responsible for the decision which flow comprises a defect, because they know what the pile is supposed to carry and how it's supposed to function. Here's something which is called a Venn diagram. With our testing, we have a lot of anomalies. Some of our anomalies are because of any irregularity in the pile, and they cause flows, the blue area. Not all flows are defects. Some of the defects are as defined by the engineers. The next item and the next instrument which we have, and this is a very recently very modern and new technology, is the BIT, borehole inclination tester. The bit is a universal instrument for testing the inclination of piles, board piles, even driven piles, even sheet pile walls can be tested with the bit, with suitable access tubes.
The square pier is surrounded by diaphragm walls. The wall elements were cast with access tubes for crosshole ultrasonic testing. The walls are 30 meters deep. Are they vertical? The bit sensor and centralizer are lowered into one of the tubes. The bit is lowered to the first stop at 5 meters. With the stop sign switched off, the bit is lowered to the next stop. The procedure is repeated all the way to the bottom. The bit is now raised, stopping at the same stations. The bit is now at the surface for final reading. The top view is now seen on the screen.
The side view is plotted on the screen in the desired direction.
The deviation of board piles is measured the same way. The verticality of second pile walls is of utmost importance. The bit can also test simple low-cost tubes for geophysical testing. Thank you for watching.
Now, the bore station is determined by almost all specifications I know of. These are the specifications of the Federal Highway Administration in America. They allow 20 millimeter per meter or 2% deviation for normal butter shafts. They allow a little more. The diagonal shafts or piles, 4%. Now, here is the bit mounted on top of a drilling bucket. It is, of course, waterproof, mud-proof, and here the bucket, while it goes inside the hole, acts as a centralizer and makes the bit follow the axis of the pile. Here you see the drilling bit, the drilling bucket, the bit is mounted on it. This is the instrument, the automatic depth meter, and this is our smartphone in our pocket that runs the whole operation and stores the data, transmits it to the cloud if necessary. We get the output. Here is a top view. We see that the axis of this specific pile or specific tube goes to the east, southeast. We have a side view in any direction. The green area is the allowable inclination of 2%. So you see that at 14 meters, we have 28 centimeters, which is allowable. As long as our axis is inside the green area, the pile is acceptable. I think the last system which I'm going to present to you is the Parralal Seismic system, the PSI. Determine unknown and unseen piles. Here you have a bridge. We have a discussion in our office if this is a crocodile or just a piece of floating wood. But of course, this bridge is founded on certain foundations. We don't know what kind of foundations there are. They may be deep foundations, they may be shallow footing foundations, we don't know. So the PSI, the parallel seismic method, is supposed to check the depths of these piles. Here is our PSI system. We have a hammer with an impact switch connected to the instrument. Here is a hydrophone, the automatic depth meter, and all the electronics are inside the cable reel. Here is how it's operated. You hit with the hammer on the superstructure. Even if you don't see the pile, you hit any point of the superstructure. The waves go down inside the foundation or inside the pile. From it, they are deviated into the ground and to the tube, access tube, which is filled with water. This is the hydrophone, which is sensitive to changes in water pressure. And the instrument or the computer monitors the depths from item 3, the depth meter, with the waves which are recorded by the hydrophone. This is the plot we get. You see that these are the first arrival times, which are arranged very nicely on a straight line. And from this point onward, here, there is a break in the slope of the line. This is where exactly where the toe of the pile is, at 18.3 meters depth. So you can test piles even if you don't see them at all. And some conclusions. First of all, in piles, defects may and therefore will occur. So I hope you didn't have any illusions until today, but if you have, you can forget your illusions. There are defects. Moreover, innovation in piling is usually accompanied by an increased defect rate. When you bring a new technology to a country, in the beginning, until engineers and contractors master the method, there may be more defects. Integrity testing techniques, which I've presented to you today, are used to discover defects before they can cause any damage. And before is a very important word here. Discovering damage after it happens is not very good engineering. Current integrity testing techniques can discover most important defects. Unimportant defects, if they are not discovered, do not interest us too much. And I must admit most. Sometimes there are defects that cannot be discovered because they are too deep in the ground, or because our most modern equipment is not capable enough. Of course, you must know the capabilities and limitations of the method you use, and, very important, test all piles. Some engineers specify testing 10% of the piles, or 20% of the piles, or 50%. This is very poor methodology. You have to test all piles. And I showed you with the PET, the pile echo tester, that testing is very fast. The testing, therefore, is also very inexpensive. So we encourage you to test all piles. Zulfikri, it's your screen.
You can speak.
You want to add
Sorry.
anything? Is it clear enough, or you want to add anything?
No, clear enough, clear enough.
Clear enough. Good. Are there any questions?
You can see the question is already arise in Q&A room.
Yes, I'll show you in a minute. Johan,
Yes.
here you go. I put the questions here, and I marked a few of them in yellow, so you can answer them.
The first question, how many meters maximum to be tested by the PETs? I hope it's the question of depth. And how many times to hit the concrete with hammer to make sure height of the pile reached, or the depth of the pile? Okay, the answer is very simple. It depends on the condition. If the pile is not very deep and the ground is not too hard, and the top is well prepared, nice clean concrete, just a few blows, 5, 6 blows, and if they are all identical, the PET takes the average of the blows and shows on the screen, and you get an excellent result. How deep can you go with the PET? I showed you the graph where the depth or depends on the slenderness ratio. This is the keyword, slenderness ratio, or the ratio between the length and diameter. And this can vary between 5 diameters to 50. Recently, I got from Thailand very good PET results from piles that were 55 diameters long. But this is very unusual. The ground there was very, very soft. Now, how to compare the use of pile testing with the dynamic analysis test method? Well, the pile testing or the integrity testing is what we call low strain testing, which means the energy we have is caused by the hammer or by ceramic rings inside the emitter of the CHUM. The energy is very small. In PDA, pile dynamic testing, we use very high energy of the pile driving hammer. Now, the waves, incidentally, are very similar in both cases and follow the same physical rules. And interestingly, the wave speed in our low strain testing, which is about 4,000 meters per second in good concrete, is the same wave speed you get when you hit with a 2-ton pile driving hammer. But otherwise, these are two methods used for different purposes. The PDA is used for establishing the dynamic capability or dynamic load you can support on the pile. And the integrity testing is checking how well the contractor produced the pile. If the building is already existing, what is the suitable method to determine the diameter length of the pile? Well, I have bad news. There is no suitable method to determine the diameter unless you start excavating and exposing at least the upper part of the pile. About the depth of the pile or the length of the pile, as I showed you, the Parralal Seismic method is the best method available today, and it can be used to establish the depth of the pile fairly accurately. Any recommendation for the installation number of access tubes? Well, in short, the more the better, of course. The more tubes, the more money it costs. Of course, on the other hand, the more tubes you have, the better your resolution. So the best is to follow the rules of the ASTM. 1 tube per 30 centimeter diameter. If inside of span pile contains water, what the CHUM can be used? The CHUM can be used only if you have access tubes, or in special cases, if you have a core drilled hole in the pile. You can also use it instead of an access tube. If you have a hollow pile, you cannot use normally the CHUM. Are there any more questions, Gadi?
It's below here. Maybe there's, I can see someone added a new one.
Yes.
Okay.
At the moment here we have an interesting question.
Okay, there are a couple of more. Let's see. Maybe you want to answer this one?
Yes, first of all, a question before I forget. I saw a question, what to do if you find a defect? As I said, this is the problem that has to be handled by a joint force of the structural engineer and the geotechnical engineer. And they should decide if the pile, there are three solutions if you have a defect. The simplest is to leave it as is. If you decide that the defect is there, but it's not detrimental to the structure. For instance, if you have a bridge pier supported on certain piles, and one of the piles has a defect, I think, and you cannot approach the pile to do any repair, you just accept it as is, and you can fine the contractor to pay for his lousy work. But in this case, you do nothing. Option number 2 is to repair the pile. There are possibilities, for instance, if you have access tubes and you have a small area down there that's of weak concrete, you can drop a dividat bar inside the affected zone access tubes and grout it. And the dividat bar will reinforce the pile where the concrete is weaker. And option number 3 is to reject the pile altogether. I don't like this option because today's piles are in many cases large diameter, deep piles, very expensive ones. And to reject the pile is just your last recourse. Don't do it unless there is no other choice. A question, which one is better, pile integrity testing or thermal integrity profiling? Thermal integrity is also really meant to check the integrity of the pile. And there is a lot of hype going around this matter, that it can be used to test the whole cross-section of the pile. And this is from research we carried out. It is a false pretense. It does not. It cannot distinguish between a pocket of foreign material inside the cage or on the periphery. So if you have necking in the pile, in the thermal profile, it will look the same as the defect that's inside the pile. And of course, for the engineer, a defect at the center of the pile is not very important as necking. The thermal profiling is another drawback. If you have any problem with the test, you don't have a second chance. If you use the PET or the CHUM and you have some doubts about the results, you can always bring in another tester or ask the original tester to repeat the test. Yes, Zulfikri. Any questions? No? Siamo?
Yeah. Yeah, enough.
Yes, two questions are the same. Is it necessary to take test the whole test site or take it from? I say the test today, the PET, the low strain impact testing is very inexpensive. Test all piles to start, and then you'll see which ones are suspect and which ones are no. And I think that covers it. If there are any more questions, you can send me by email, and we'll post the results on the website or on our website.
Yang mau bertanya langsung mungkin boleh angkat tangan Pak, itu ada pilihannya. Nanti biar dikasih akses buat bertanya langsung. Atau yang malu-malu bisa ketik Pak di room Q&A. Silakan. Bisa raise hand kalau ada yang mau bertanya langsung. Tapi dalam bahasa Inggris ya Pak. Mr. Joram, you see many questions in the Q&A room. Maybe you can answer each of them.
We have already. What is the difference?
Enough. If any people raise hand, maybe consider to give him to speech, maybe to ask directly. If any raise hand.
There is a question, I think I covered it in my presentation. What's the difference between flow and defects? A flow is any change in the composition or in the form of the pile, anyone, large or small. Defect is a flow that affects the performance of the pile. So it's a special case of a flow. That's a defect. A defect calls for action on the side of the engineer. They have to do something about the defect. We are engineers, we are paid for making decisions, aren't we? I'm like politicians. Those? Okay, Zulfikri.
Yes, maybe Gadi, maybe better if you answer one question, you say the number of the name who is asked a question and read the question and then answer. So
The names?
who has a question?
Zulfikri, we had many questions and we answered about 10 of them, and the time is about to end. We'll be happy to answer all other questions in writing.
Yeah, no problem.
Other ways. And there are about 40 questions, so we cannot answer all of them.
Yeah.
Okay.
Yeah, Gadi, it's already our tradition to make a resume of the webinar, including the question and answer of each of the question from each of them, and we will distribute to all of them.
Okay.
Later on. Okay.
Okay. Thank you.
Yes, Mr. Joram, thank you for your presentation. Gadi and team.
Thank you
Thank you for the presentation, Bapak-bapak, ibu-ibu semuanya. We think that the time is already end, ya, almost end. So yeah, so I I say thank you to you, all of Piletest team in UK and also in Tel Aviv, everyone there, and thank you for everyone who joined this session of webinar. Bapak-bapak, ibu-ibu, terima kasih kehadirannya di webinar kita yang keempat ini. Panitia, mohon maaf banyak kendala di mungkin yang teman-teman ada yang suara tidak jelas mungkin, atau room ini memang sebenarnya di order untuk lebih dari 200 ya, ternyata yang terpesan 200, jadi cuma 200 partisipan yang join. Next kita jadikan sebagai perbaikan untuk ke depan. Kami akan share materi dan yang butuh sertifikat nanti dari teman-teman yang sudah terikut acara, kontak panitia akan kita sediakan, dan kami akan share nanti jawaban dari setiap pertanyaan dan juga video link dari webinar kita hari ini. Thank you, Mr. Joram. Thank you for everything. Thank you for participants. We from Testindo, thank you, and we hope we can meet in other session.
Yes, in person. Thank you and bye-bye.
Bye-bye. Thank you, Zulfriqi.
Yeah, bye-bye.
Bye. Well.